All right. Well, it's kind of hard to believe, but it is well, I don't know if it's hard to believe, but it's week 3 Thursday, and I think the part that's hard to believe is that this means we are halfway done with our course after today's lecture. That's the halfway point, and then we've got another 3 weeks, and that's it. That's a 6-week session. It goes by very quick. So anyway, today's lecture is all about, we're going to talk more on hypothesis testing. We're going to do a kind of a conceptual deep dive on hypothesis testing, and that's what we will take a look at that. I guess before I get into this, just kind of want to do a quick check-in, see how I don't know, course things are going, how the homeworks, labs, quizzes. Any comments or concerns or anything to say there? Or do you feel like so far it's okay? Okay, there was a subtle nod and a few thumbs up here. So, I mean, all right, well, I'll take it. And that's it. Okay, homework is especially helpful for the quizzes. Okay, well, great. I will continue to assign homework. So, and yeah, so as we get into hypothesis testing and all of that, I think the quizzes, as far as the difficulty of the quizzes, my aim has been to kind of be like around, some of the homework problems are easy, some of the homework problems are hard, and my aim is to make the quizzes kind of like in the middle, not too hard, not too easy, just kind of straightforward. Like if you did your homework and if you looked at the notes, then hopefully you would do well in the quizzes. And I continue to have that aim for future quizzes, but there's just more kind of like moving pieces in these things with the hypothesis tests. Like you have to get this hypotheses and you have to do the standard error and you have to look it up in the reference table and you have to calculate areas and p-values and make a conclusion. There's just kind of a few more things involved, and so it's easy to make a mistake in one of these kind of sections or parts of the question. So I guess just be mindful of the entire process and try to kind of stay focused throughout the thing, and hopefully the quizzes will continue to be of an appropriate difficulty, but I just want to kind of give you a heads up and warn you that these topics now there's a few more parts involved. So we left off on Tuesday and we talked about the t-test and a fair amount of detail on Tuesday, and so just to kind of recap and summarize what we established regarding the t-test, we said we start off, we write off our hypotheses, right? And the hypotheses are kind of these concepts or these ideas, and we're going to test them. We test our data, that our hypotheses against the data that we've observed. And we start with our null hypothesis, which always has an equal sign. And as far as the t-test goes, the null hypothesis is always going to be that the mean of population 1, mu1, is equal to the mean of population 2, mu2. The alternative could be mu1 is not equal to or greater than or less than mu2, okay? And we said if the null hypothesis were true, if we make that assumption that the null hypothesis were true, then we expect the sample means y bar 1 and y bar 2 to be similar to each other. We expect those two values to be similar. And what we do is we calculate a test statistic which measures how different y bar 1 and y bar 2 is from each other in our observed data. So we take that difference, y bar 1 and y bar 2, between y bar 1 and y bar 2, and we measure that difference in terms of standard errors. So kind of like a z-score, but this time we're going to just take that difference and divide by the standard error, which is a little bit more involved. The formula for the standard error is a little bit more involved than just the standard deviation, but but it's there. And then once we do that, we're going to look up this test statistic in the t-table using, degrees of freedom, n1 plus n2 minus 2 as an approximation to get a sense of how unusual this difference is. And when we look up the test statistic, we try to find the area in the tail beyond whatever TS is. So whether that's, the area, if you have a positive TS, you're looking for the area beyond that, or a negative TS, you're looking for the area beyond that to the left, or maybe you have a two-sided test and you take both of those areas, whatever you get, that's going to be our p-value. And so we have this definition for the p-value, and this is kind of an important term, and that is that the probability of observing the statistic in our data, or the p-value is the probability of observing the statistic in our data or something more unusual, but it's under the condition that we assume that the null hypothesis is true. So if we assume the null hypothesis is true, it's the probability of getting the data that we have, basically the test statistic in our data. And for our t-test, and this is going to be different for all the other tests that we will encounter later, is that the p-value in the area is the area in the t distribution that's in the tail or tails beyond the test statistic. And so, once again, we start off with a null hypothesis that makes some kind of claim about the population. And in the t-test, it states that these two means, the means of the two populations are exactly equal. Hold on, we have a question. It says, if your t-value ends up being in the far right or left of the table, do you just do p is greater than or less than the number instead of doing a range of values? Yes. So that's a good question. So the question is, what do you get if let's say your test statistic ends up being, say, I don't know, like 30, just some really, excuse me, really extreme value, right? So here is our t-table, and let's just say we get a really big number, like let's say 20 degrees of freedom, or however many degrees of freedom, you get a big number like 30. Okay, and so 30 is farther from 0 than any of these numbers in this last column. So if we're in 20 degrees of freedom and our number's 30, we don't really know the area in the tail, but we do know that whatever it is, it has to be less than 0.0005. Okay, so we don't know exactly what it is, but we do know it's less than 0.0005, and we can just leave it there. Okay, and then the flip side is also true. Let's say your test statistic ends up being really small, like 0.1, right? 0.1. So 0.1 is very close to 0. It's a lot closer to 0 than any of the values in this column. So this column, the smallest value is like 0.8 or something. And so we're closer to 0 than that. And that just means the area beyond t, the area in the tail is going to be whatever it is much greater than 20%. Okay. And so that's what your answer would be. So you just kind of look at this and you just kind of, you would have a limit on one side. You'd say, well, we know it has to be greater than 20%, or we know it has to be less than 0.005. Okay. On the other hand, if you can also use R as a calculator to get, slightly more precise value, but that's fine. Okay. All right. So coming back to here, in the t-test, the null hypothesis states that the means of the two populations are exactly equal. We test that hypothesis against our data, and in doing so, we're going to calculate our p-value. And basically, when we make our conclusions, we compare the p-value from our calculations to whatever significance level we've chosen. So perhaps we've chosen, significance level 5%. That's a common choice, but sometimes you can go with a smaller one, sometimes maybe even a larger one. And basically, if the p-value is less than alpha, we say that our p-value is small, and that's going to lead us to reject the null hypothesis. If the p-value is greater than alpha, the p-value is said to be large. So again, when we say that the p-value is small, okay, ultimately the conclusion is that our decision is to reject the null hypothesis. The reason for that is that when we get a small p-value, that means the test statistic that we've observed is extreme, right? The difference between y bar 1 and y bar 2 that we've actually observed in our data is considered to be large, compared to the standard error. And this means that if the null hypothesis were actually true, it should be very unlikely for us to get this difference. But then the fact that we actually did get this difference, which should have been an unlikely result, indicates to us that this null hypothesis assumption is wrong. And so therefore, if we end up with this extreme value, end up with a small p-value, our decision is going to be to reject the null hypothesis. Now, we want to keep in mind that it is technically possible that the null hypothesis actually is true and that we did get that unlikely scenario by random coincidence, right? So you can do your calculations and you say, you know what? The probability that this happens is really small and therefore we're going to reject it. But it could be that you just got that really weird, really low probability circumstance, that you just happen to get that unlucky situation and you make the wrong conclusion, right? We're willing to reject this possibility because that probability is small, but we do have to kind of keep in mind that that's a possibility. I mean, for example, somebody says, go to that, grab a deck of cards, draw a random card, and the card you're going to draw is going to be the 5 of diamonds. Okay. And let's say you grab a deck of cards and you pull out a random card and it turns out to be the 5 of diamonds. Okay. Now, would you say, oh, that was a really lucky guess? Or would you say, oh, you must have done something tricky in order to get me to draw that 5 of diamonds? And you'd be confused and you'd probably be amazed that this happened. But I think your conclusion would be that, your friend did something to set this up rather than making a lucky guess. Okay. Now, could your friend have just had a lucky guess? And the answer is also, that's a possibility, right? He's got about a 1 in 52 chance of just making this lucky guess that you're going to draw the 5 of diamonds. We're willing to kind of ignore that because the probability of that happening is only 1 in 52. And we're saying, that's small enough for me to kind of just say, I don't think it was this random scenario where, there's this probability that it could happen, but rather we're going to come to the conclusion that, he did some kind of trickery, whatever it is, to get me to draw this card. The flip side is you do your calculations, you end up getting a large p-value. And if so, the p-value is large, that means that our observed data, whatever our test statistic is, could be easily produced by randomness, right? While the null hypothesis were true. This would be just kind of like your friend says, draw a random deck of cards. I bet the next card you draw will be red, okay? And you draw a red card and you just say, yeah, that was probably just a lucky guess. I'm not gonna presume that you've got some magical powers here, okay? And so even if our observed data doesn't match the null hypothesis exactly, it's not considered to be an unusual outcome. So even if we don't have 2 sample means that are exactly equal, whatever we observed, that the difference we had is small enough that it's not considered to be unusual. And so when we end up with a large p-value, our decision is going to be not to reject the null hypothesis. Now we have to be careful, and we are not allowed to say that we accept the null hypothesis. And I'll get into this, but that's kind of a key thing in statistics, is that you say we do not reject the null, but you cannot say that you accept the null. You are allowed to say you accept the alternative, but you cannot say you accept the null. All right, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter E. E as in elephant or errors. E is your first view quiz answer for today. Now, when you do hypothesis testing and you do statistical inference, whatever it is, anytime you're trying to make conclusions about the population based on only a sample, there are errors that are just inherent to the process, okay? We cannot completely avoid these possible errors just because the fact that we are making a conclusion about the entire population based on only a sample, right? So the fact that we don't have all the data just means that occasionally we're going to make a mistake. And so the two types of errors are this, right? The first kind is the the type 1 error, and the other kind is the type 2 error. This is kind of funny, is that when statistics was being first kind of developed, this framework of hypothesis testing was first being developed, they realized, oh yeah, there's two errors that are inherent to the process and they can't be avoided. And they didn't have good names. They just said, all right, the two types are type 1 and type 2. Later on, we came up with better names, the false positive and the false negative. But unfortunately, the names for type 1 and type 2 error have kind of stuck around in the literature. And so we still refer to these things as type 1 and type 2 error, but they are admittedly terrible names. So the type 1 error is the false positive, okay? And that means, something sends up a red flag, right? And you say, and you're going to reject the null hypothesis, right? You end up getting a difference. It's pretty big. And you say, I've got to reject the null hypothesis. But in reality, the null hypothesis was true, and it shouldn't have been rejected. That the difference that you have observed that sent up these red flags, that was just kind of a weird coincidence type of thing. It was just random chance, unfortunate circumstance of the data that you ended up observing a large difference, and you think the two populations have a different mean. Okay. The type 2 error is kind of the flip side. It's the false negative. You don't believe that, you do not reject the null hypothesis. So you observe some kind of difference, you do your calculations, and you say, oh, the probability of getting this difference isn't that that low, so I am not going to reject the null hypothesis. But in reality, the null hypothesis actually is false, and you should have rejected it. So, in the context of the t-test, we're talking about population 1 has a different mean from population 2. So in reality, that's the case. Population 1 has a different mean from population 2. But when you took your samples of data, maybe sample 1 had, a mean of 50, and sample 2 had a mean of 53. And that difference of 3 just wasn't significant enough to kind of set off any red flags. And so you say, well, I'm not going to reject the null hypothesis, but in reality, you should have. So that's the type 2 error. So that's the false positive and the false negative. Okay. So, so type 1 error, yeah. So a little bit more detail. Let's say, you go through your process, you end up with a p-value of, say, 4%. Your significance level is 5%. And so according to the process, you say, because 4%, my p-value is less than the significance level, I'm going to reject the null hypothesis. You conclude that the null hypothesis is wrong, you reject it, okay? And then, but you go and later on, maybe you gather more data, you find out more about this, and it turns out that the null hypothesis actually is true, and the data you observed was just some random fluke, right? You just happen to get some difference, a difference between sample 1 and sample 2. The difference was 8, and that seemed really strange. And it was just some strange random outcome, okay? And so the decision to reject the null hypothesis, when in reality it was correct, is a type 1 error. That's a false positive. And the type 2 error is just kind of the opposite, where the p-value ends up being big. You're bigger than your significance level. And so you do not reject the null hypothesis, but it turns out that the null hypothesis was wrong and you should have rejected it, okay? This often happens just because you didn't collect enough data, right? So if you don't collect enough data, let's say your sample size isn't large enough, okay? You're often going to get a p-value that's large, okay? Sometimes the random flukes just work against you, right? In reality, population 1 has a larger mean than population 2, but just by some random fluke, when you took your sample from population 1, you happen to get a sample where the values were small. And when you take a sample from population 2, you happen to get a sample where the values were big. And so overall, when you compared sample 1 and sample 2, they looked to be comparable in size. And so it leads you not to reject the null hypothesis, right? Or, you know, if we're talking about some kind of coin, maybe you have a trick coin that should land heads more often than tails, but again, because it's random, you know, when you flip it 20 times, you get 10 heads out of 20, and there's nothing there that says, oh, you know what, this is a trick coin. It looks like a fair coin based on this sample of data. But perhaps if you gathered more data, you would have realized that it's a trick coin or something like that. Okay, so that's the type 2 error. So just, you have this table. This table also appears in your textbook. The truth being, if the null hypothesis is true and you decide to reject the null hypothesis, that's our decision, that's a type 1 error or a false positive. If the null hypothesis is true and your decision is not to reject it, that's the correct decision. And then over here, if the null hypothesis is false in reality and your decision is to reject it, that's the correct decision. That's what we want to do. If the truth is that the null hypothesis is false and we decide not to reject it, that's the type 2 error. That's the false negative. And so, we say, okay, well, we want to avoid these types of errors, right? And how can we do that? Well, the significance level that we choose, the alpha that we choose, is equal to the probability of committing a type 1 error. So if we choose alpha equal to 5%, then we are saying I am willing to make a type 1 error 5% of the time with a risk of 5%. Okay, so we accept this risk of making a type 1 error 5% of the time. Okay. You can reduce your risk of type 1 error by choosing a smaller alpha. You can say, well, I don't want to make a type 1 error 5% of the time. I want to only make a type 1 error like 1% of the time, or 1/2 of 1% of the time. And you can do that. You just choose a smaller alpha. Okay, you pick a smaller alpha. So you might say, well, why don't I just pick a small alpha as possible, right? Why don't I do this? Well, if you do that, the consequence of that is that you are going to need a massive amount of data before you reject the null hypothesis, right? So it's the difference between becoming overly cautious to make your conclusions, right? So we talked about the difference between a 95% confidence interval and a 99% confidence interval, and we said if you're willing to be only 95% confident, you can kind of reject certain values. If you want to be 99% confident, then you have to be more cautious, and you're not going to be rejecting all of these values. And so if you want to be, if you really want to reduce the risk of type 1 error, you can choose a very small alpha, but then you're going to be extra cautious, and you will hardly be rejecting any values, and you would need an inordinate amount of data before you start to reject the null hypothesis. So the downside of picking a really small alpha is that you are going to increase the risk of a type 2 error. You need a lot more evidence before it convinces you to reject the null hypothesis, and that's going to increase the risk of a type 2 error, because now there's going to be more times where you should have rejected the null hypothesis, but because you were being overly cautious, you didn't. Okay, and that's the type 2 error. And so as the researcher, you get to choose what level alpha you want to use. Okay, and really, we often use 5% alpha. That's kind of the choice, but I think that choice of 5% alpha has come under a lot of fire, justifiably so, because this process of choosing your significance level should depend on the situation. And you have to think, what are the consequences of making a type 1 error? And what are the consequences of making a type 2 error? And depending on the situation, the consequences of a type 1 error could be more severe or less severe than making a type 2 error. And then depending on those cases, you would want to adjust how large or small your significance level alpha is. Okay, so you don't want to be too cautious, because if you're too cautious, you're going to miss times where you should have rejected the null. Okay, so here's here is just a couple scenarios. So one scenario is a patient visits a doctor for a disease screening, right? And so generally, the doctor is going to assume patients are healthy unless they show symptoms of illness and, you know, some kind of test results or something. So our null hypothesis here is that the patient is healthy, and our alternative hypothesis is going to be that the patient is sick. And ideally, what we want is that everyone who is healthy will get cleared, and, you know, we send them home. We say, you're healthy, you got nothing to worry about. And anytime somebody is sick, we detect that and they get medical attention, right? So either we prescribe them medications, or, you know, we admit them to the hospital for, you know, whatever it is, they get medical attention or something if they're sick, okay? What would a type 1 error be, and what would a type 2 error be in this scenario? Okay. A type 1 error is the false positive, and that would be a healthy person ends up getting medical attention, that somebody is actually healthy, but the doctor believes they're sick and needs medical attention, and, you know, they get admitted to, you know, the hospital, or they, you know, something like that happens, okay? The type 2 error is the false negative, where somebody is actually sick, should be getting medical attention, but they are sent home. They say, ah, you got nothing to worry about, okay? So in this scenario, what would we say is, which type of error is worse? The type 1 or the type 2 error is the worst type of error to make here? Yes, I agree. The type 2 error would be worse than the type 1 error, right? The type 2 error is worse than the type 1 error. And so in order to avoid a type 2 error, okay, we are going to pick a large alpha. We are more willing to make type 1 errors, okay? We're more willing to make type 1, and we want to avoid type 2 error. So we're going to choose a large alpha. And this means it only takes, you know, a little bit of evidence for us to reject the null hypothesis, okay? Now, all right, I don't know if you guys ever use the website WebMD. So, you know, online there's WebMD, and I think there's some jokes and memes about WebMD, kind of like anytime you type in, you know, your symptoms, WebMD comes back and it says, you might have cancer or something like that, right? You might, you know, and it just lists off all of these potential diseases and all of these things. And it's very kind of frightening. They say, don't type your symptoms into WebMD unless you want to be scared about what could be wrong with you. And it's not that WebMD is trying to scare you or anything like that. And it's not like this huge conspiracy where, because frequently WebMD will say you should go see the doctor. And it's also not some huge conspiracy where they're trying to just artificially increase people to visit the doctor's office so that, you know, these doctors get more money and things like that. It's just that WebMD is operating with a very large alpha, right? What they are trying to avoid is they're trying to avoid the type 2 error. They don't want somebody to type in their symptoms where they actually have an illness, they actually have a disease that requires medical attention, and they think that they're okay. They want to avoid that scenario. So they're willing to make the type 1 error more frequently, which means, you know, they say, hey, it could be this, you better go talk to a doctor, okay? Because for WebMD or any kind of website like that, the consequence of a type 1 error is, you know, just a little bit of maybe psychological anxiety, but you can't go to the pharmacy and say, you know, I typed my symptoms into WebMD and I need you to give me these medications, right? The drugs and medications are kind of held behind, you know, you have to see an actual doctor, you have to get an actual prescription and things like that. And so WebMD operates with a very large alpha, and basically every kind of successive step, every time the consequence of a type 1 error gets worse and worse, that level of alpha goes farther and farther down, right? So, you know, for example, if the treatment is surgery, and that's an extreme kind of treatment, the doctor is not going to just prescribe surgery to you immediately. You know, you walk in and you complain about a pain on your back. They're not going to say, okay, we need to give you surgery. You know, if you know, there could be a reason for getting surgery or something, but there's going to be a series of tests, right? They're going to do some imaging. They're going to do all kinds of, you know, other kind of radiology type of things to make sure that surgery is the correct choice, the correct treatment, because, you know, the consequence of doing surgery for somebody who doesn't actually need surgery, that, you know, that's much, much worse. So to kind of avoid that type 1 error, you know, there's successive, you know, tests, right? You know, other things like extreme, you know, chemotherapy for treatment of cancers, you know, this extreme medical, you know, medicinal regimen that's very hard on the body. And they're not going to just kind of prescribe that and say, this is what we're going to start just based on somebody's speech. They're going to do, you know, a series of tests and biopsies and things like that to kind of confirm that this is the correct treatment. So as far as WebMD goes, they're operating with a very large alpha, but before you start any kind of serious medical treatment, you know, the level alpha gets further and further lower to kind of make sure that indeed this is the correct treatment here. Okay. Here's another scenario. We can think of a criminal trial, and you know, we will say we assume defendants are innocent until proven guilty. When I was younger, there was a TV show called Cops, and it was always like they followed these you know, police officers around, and they would, you know, just arrest people and things like that. And it was popular when I was a kid. I don't think, I can't imagine a TV show like this being popular today. But at the end of every show, they would always say, you know, everyone, you know, all defendants are presumed innocent until proven guilty. And this is how our criminal justice system is set up. Okay. And so we're going to say our null hypothesis is that the defendant is innocent. This is what we are assuming. And it is up to the prosecution, you know, kind of your district attorney, to kind of present enough evidence to the judge and the jury that the defendant is guilty, that the, you know, whoever is on trial actually committed the crime. And if the prosecution does not have enough evidence, then the correct decision will be to let the defendant go free. That, you know, we do not want to be convicting innocent people. And so, you know, ideally, every time there's a trial, anybody who is innocent will be acquitted, will not, will be let go. And anyone who is actually guilty will be convicted. That's what we want, okay? If we think about what is a type 1 and a type 2 error, we want to avoid both of these things. Both of these things we would say would be a failure of justice. A type 1 error would be a false positive where an innocent person is convicted, sent to prison, or possibly worse. A type 2 error is a false negative where a guilty person is let go. Now, again, we want to avoid both of these things, but if we had to decide, you know, which of these errors are worse, you know, and this, I guess there's always a little bit of debate here, you know, functionally as a society, who do we want to be? But I would say that the type 1 error is worse, that convicting an innocent person is worse than letting a guilty person go. You know, we could probably imagine some high profile cases. A lot of times we see these, sometimes cases on trials go to TV, and there's a lot of, I don't know, media attention. In a lot of these cases, sometimes there's a not guilty verdict, and people are outraged, you know, rightly so. But then the opposite of convicting an innocent person, I think, is also a terrible thing. So in this situation, we would say a type 1 error is worse than a type 2 error. And that means in order to kind of avoid the type 1 error, to reduce our chance of a type 1 error, we are going to work with a small alpha. We're going to pick a small alpha. Okay. And that means it's going to take a lot of evidence, a great amount of evidence. And kind of the key phrase that we hear, you know, at least in courtroom dramas, is, that it should be beyond a reasonable doubt, that, whatever the suspicion that you have as a member of the jury must be beyond a reasonable doubt to come to that guilty verdict, okay? To reject the null hypothesis, to reject that the idea that the defendant is innocent, we want to have a large amount of evidence, and we don't want to be convicting people just based on a small amount of evidence or just some kind of gut feeling or a hunch or suspicion or something like that. Let me see. We cannot actually avoid type 1 error completely though, okay? And maybe I could add another slide here, but the idea of completely avoiding a type 1 error is not possible, okay? Because in order to completely avoid type 1 error, the only way you can do that is to have alpha equal to 0, all right? The only way you can completely avoid type 1 error is to have alpha equal to 0. But if alpha equals 0, then what is your conclusion going to be every single time? Alpha equal to 0 is going to be, means that you will never reject the null hypothesis. You will never reject the null hypothesis. You will always say, we don't have enough evidence to reject the null hypothesis if you have alpha equal to 0. And so, we could imagine some, scenario where, a judge convicts someone, sends them to prison, and then later on, new evidence emerges, and it turns out that this person was innocent, right? And the judge feels very guilty and says, I never want to do this again. I never want to convict an innocent person. I never want to send an innocent person to prison. And I think that's a reasonable thing to feel. But then if the decision there is to say, well, I never want this to happen, the only way a judge can guarantee that an innocent person will never be sent to prison is to never send anybody to prison, okay? That would be the only way to completely avoid this. And at that point, then that person is no longer a judge. That person's just basically a not guilty verdict, just kind of a rubber stamp that just says, okay, you're free to go. And in that case, that's also kind of a failure of the justice system. And this is an argument that there's always some debate about whether or not as a society we should have capital punishment. Should we as a society execute people who are guilty of terrible crimes? And one of the arguments against it is that the idea of executing an innocent person, to kill an innocent person, is a great crime of society. And the only way you can guarantee that this will never happen is to never execute anyone, right? And there have been cases where people have been convicted and sent to death row, and before their actual execution, new evidence has emerged that exonerated them. And they said, this is, the cost of this is too great as a society to bear. And so, there's always debate about, whether or not, and this is not what I'm trying to get into, but it's the idea that if you want to completely avoid type 1 error, the only way you can 100% avoid type 1 error is to never reject the null hypothesis. But then, that's not very effective either. Here's a little bit of, I guess, humor, stats humor, I guess, if there's such a thing, okay? And so you can assume that in the null hypothesis, we're going to assume that the patient is not pregnant. And so the type 1 error, the false positive, would be the doctor telling this man who is clearly not pregnant that you are pregnant. And the type 2 error would be, this doctor telling this woman who is pregnant that she is not pregnant, right? So medically speaking, probably a type 2 error is worse. We want to make sure that somebody who is pregnant is getting the medical attention and, doing the things necessary to kind of ensure the birth of a healthy child and things like that. On the other hand, in a conversation with a friend, making a type 1 error, assuming somebody is pregnant when they are not, is considered to be a very potentially friendship ending error. So that would be our bit of stats humor here. As far as these values go, we've got alpha, which we talked about, and that is our significance level. That is the probability of making a type 1 error or a false positive. And then we have another letter. We have beta. This is the Greek letter, the second letter of the Greek alphabet, beta. And that is the probability of making a type 2 error or a false negative. And so, you know, alpha being the first letter, looks like the A is type 1. Beta being the second letter is type 2. That's how we can remember it. And that's actually alpha and beta. That's where we get the word alphabet. We just kind of put those two letters together, alpha and beta. And the flip side of that, the power of a test is 1 minus beta. Okay, so if we think of beta being the probability of making a type 2 error, then 1 minus beta, you know, 1 minus the probability is the probability of the complement. So what is the complement of a type 2 error? So the power would be equal to the probability of not making a false negative. Now that's a weird sentence to say, right? Probability of not making a false negative. Okay, what that means is it's the probability of correctly rejecting the null hypothesis when you're supposed to reject the null hypothesis. Okay, so it's a good thing. It's the probability of correctly rejecting the null hypothesis when you're supposed to reject it. Sometimes we call this the test sensitivity. You know, how sensitive is the test to make that correct decision, right? And so, excuse me, you know, a year, you know, I guess a year and a half ago when the coronavirus was starting to, you know, spread and things like that, there were, before vaccines were developed, a lot of focus was on just kind of testing for the coronavirus. And there were questions about, you know, how sensitive are these different types of tests? You know, there was the, you know, antibody test and the molecular test and different kinds of tests. And different tests have different sensitivity rates, meaning that if somebody actually had the virus, you know, will the test actually detect it? And you know, in some cases, it wasn't sensitive enough that if somebody was just infected maybe the day before, their body had, you know, the virus hadn't had enough time to kind of produce, you know, reproduce itself enough to be detected. And, you know, the test was only, you know, effective or sensitive enough after, you know, a person carried the virus for a few days and things like that. And so we would say, you know, a test is powerful or sensitive if you are confident that it will correctly reject the null or, you know, detect a disease when it's supposed to, right? So, you know, we want powerful tests. We want tests that will kind of correctly detect a disease or correctly reject the null when it's supposed to. We have, oh, okay. The t-test and the confidence interval that, that we looked at, I guess, last week now, they are mathematically equivalent, okay? So a hypothesis test where your significance level is 5% is equivalent to making a 95% confidence interval. So whatever conclusions you would make from a 95% confidence interval, you know, should we reject this value or not, would be the same conclusions that you would make if you conducted a hypothesis test at the 5% level. And similarly, if you do a hypothesis test at the 1% level, it would be equivalent to conducting a 99% confidence interval, right? And kind of the general trend is just whatever alpha level you have here, it's equivalent to making, you know, basically a 100% minus that number confidence interval. So if you have a alpha of 10%, that would be like a 90% confidence interval, and so on and so forth. So, you know, if your hypothesis test for some data ends up with a p-value less than alpha, you would reject the null and conclude that mu1 is different from mu2. Similarly, if you make kind of a 1 minus alpha confidence interval with the same data, you would make the same conclusion that mu1 is different from mu2, right? And for that to happen with a confidence interval, that means the confidence interval does not contain the value 0. So let's just look at some scenarios here. Let's say we perform a hypothesis test with alpha equal to 5%, and our conclusion is that we do not reject the null hypothesis, okay? And I've intentionally left presented as minimal information as possible. So what do these statements here say about our p-value? We chose not to reject the null hypothesis, so all we can say for sure is that our p-value, whatever it is greater than alpha. It's greater than 5%. Okay, so we don't know the exact p-value, but we do know that it's greater than 5%. And so here I have a series of questions. What would happen if we used the same data, the same test, but I had alpha equal to 1%? What would happen if we use the same data and same test, but we have alpha equal to 10%? If I make a 95% confidence interval for the same data, for mu1 minus mu2, will that confidence interval contain 0? What about a 99% confidence interval? What about a 90% confidence interval? Will any of those contain 0? So why don't I give you guys a minute to think about your answers to these questions? And your choices are, for here, it would be, we would reject the null, or we would not reject the null, or we don't have enough information. And here your answer is either it contains 0, it does not contain 0, or we don't have enough information. So why don't you guys take a minute here and think about your answers to these questions. Okay, I'm gonna go ahead and pause the recording. All right, let's let's take a look at what our responses might be. So I guess I'll go through each of these here. So what we know is that our p-value, we don't know exactly what it is. We know it's greater than 5%. So our p-value could be something like 7%, it could be 10%, it could be 20%, who knows? Okay, so we just know it's bigger than 5%. If we use the same data, same test, but this time alpha was 1%, we know our p-value is going to be greater than 1%. So our conclusion here for this first question is that we're not going to reject the null hypothesis. Okay. But what if alpha is 10%? Okay. Well, the answer here is that we don't have enough information. We don't know exactly what the p-value is. The p-value could be 7%, and we would reject it here at 10%. Or the p-value could be like 22%, and then we wouldn't reject the null hypothesis. So we're not sure. So the answer to the second one is we don't know. Okay. If we make a 95% confidence interval, will that confidence interval contain 0? Okay. So over here, 95% confidence interval is equivalent to running a hypothesis test with 5% alpha. So if our conclusion with the 5% alpha is not to reject the null, the corresponding confidence interval will also come to the same conclusion, that we are not going to reject the null. And so in order for us not to reject the null, that means our confidence interval has to contain 0. That 0 is somewhere between the ends of our interval, and that means we are not going to reject it. Okay. And so if we think of this, our 95% interval, whatever it is, contains 0. Let's make a 99% confidence interval. Okay. The 99% confidence interval is just going to be wider than the 95% confidence interval, right? So you think of 95% confidence interval, 99% confidence interval is going to be wider. If the 95% confidence interval contains 0 and I make it wider, this wider interval will also contain 0. So it will contain 0. We are not going to reject the null. Same conclusion as making alpha equal to 1%. On the other hand, with the 90% confidence interval, here's our 95% confidence interval. If I make a 90% confidence interval, then it's more narrow. And when we make our interval more narrow, it's possible that you could have 0 between here and here, but then when you make it more narrow, it's possible that 0 is outside of the interval. But it's also possible that 0 remains inside the interval. So we're not sure. So will the confidence interval contain 0? The answer to this one is we are not sure. So here, we do not reject, we may or may not reject, it would contain 0, the 99% confidence interval contains 0, and the 90% confidence interval may or may not contain 0. And so those are your answers there. Okay, you can expect to see maybe a handful of questions like this appear on your quiz this week. So just a heads up. I think it's worth noting and talking about association and causation once again. I know I talked about this, on our first day of class, where we said, you can, from an observational study, you can only make a conclusion of association. If you want to make a cause and effect conclusion, you have to look at a randomized experiment. Okay, so when you do a t-test, at the end of your study, you might find an association basically between your grouping variables and the response variable, right? And I haven't really been referring to these things as grouping variables and response variables. But basically, the variable that you're measuring, the values that you have, that's going to be your response variable. That's the number you have. And basically, whatever you have that separates population 1 from population 2 would be your grouping variable, right? And so at the end of your study, you might make the conclusion that the mean of population 1 is larger than the mean of population 2. And we would say, there's an association between that grouping variable that distinguishes population 1 from population 2, whatever it is, right? It could be a grouping variable based on gender, or a grouping variable based on, treatment, whether it's treatment or placebo, right? So that could be population 1 versus population 2. That's one variable. And then you're measuring whatever outcome it is, the height of the people, or, blood pressure after taking medication, whatever it is, that's your response variable. And maybe you find some kind of association there, right? And again, association does not mean causation. It could. And, if you find an association, it's worth investigating it more to see if there is a cause and effect relationship. But at best, just remember, if it's an observational study and you're only kind of observing things and you don't have control over assigning treatments or assigning different conditions, then all you can do is make an association, a conclusion about association. If you want to make a cause and effect conclusion, you need to conduct a randomized experiment where you kind of control, these other aspects of variation and things like that. So just keep that in mind. There's the reading in the textbook, I think, is pretty good, covering this subject as well. Okay, we're gonna look at one more section in chapter 7, and this is on non-parametric tests. And I'm kind of deciding how much I want to get into this, but but the t-test that we've been covering and describing in great detail today, and on Tuesday as well, is considered to be a parametric test. Okay, the mathematical theory behind the t-test is based on the central limit theorem, right? That the t-test, excuse me, says that the sampling distribution can be approximated with a normal distribution. And if you think about the normal distribution, you have the parameters, the mean and the standard deviation. And any kind of test that depends on this theoretic distribution that has, these kind of parameters and stuff is what we call a parametric test. So later on, we'll learn more parametric tests like the chi-squared test and ANOVA and things like that. And they all have kind of these corresponding theoretic probability distributions. And if you're interested, or if you were a statistics major, you would take kind of a mathematical statistics course, and you would kind of prove some of these mathematical concepts and things like that. That's beyond the scope of our course, but just it suffices to say that these are parametric tests. Now, in order for us to use the t-test and apply the central limit theorem, there were a couple conditions, and I think I talked about this on Tuesday, but I'll just kind of reiterate them here. is that the samples, they have to be collected independently and randomly. And your sample size has to be large enough. And we said, you know, if the population is normal, then any sample size is large enough. But if the population is not normal, then you want a sample size of around 25 or more. That's kind of your rule of thumb. And if these conditions are met, we can apply the central limit theorem, and that says we can assume that the sampling distribution follows a normal distribution. But on the other hand, if these conditions are not met, then using the t-test in these situations could lead us to the wrong conclusion, right? And you know, one could argue, and probably I would argue this, that making the wrong conclusion would be worse than making no conclusion, right? So, so in these cases where you can't apply the central limit theorem and you shouldn't be using the t-test, we have an alternative, and this is called a, well, we have kind of a family of alternative tests, and these are non-parametric tests. Non-parametric tests don't use the normal distribution or don't use these parametric distributions. And you can take an entire course on non-parametric statistics. There's kind of a whole subfield of statistics that work on non-parametric statistics that make kind of minimal assumptions about sampling distributions and things like that. And as far as our class goes, I think we'll learn just one test. Maybe I'll do another one next week. I'm not sure. I'm still kind of debating the content regarding non-parametric statistics. But our first one that we're going to learn is called the Wilcoxon-Mann-Whitney test. And that's the name of 3 people who were involved in kind of the development of this test. Is actually kind of, there was Wilcoxon who developed it, and then Mann-Whitney developed kind of a similar and equivalent test, and they didn't realize it was the same until like later. So anyway, this is the Wilcoxon-Mann-Whitney test. And we use it in similar situations to where we would use a t-test, where you basically have 2 populations and you want to see if these 2 populations are different. Now with the t-test, we said population 1 has mean 1, population 2 has mean 2, and we want to see if those means are equal. When we're talking about the Wilcoxon-Mann-Whitney test, we have these 2 populations, but we're not going to use terms like the mean. Okay, the mean is a parameter of the population. And the whole idea of a non-parametric test is that we're not involving parameters. So we're going to keep it, we're going to make a vague statement, and we're going to see if the 2 populations tend to produce different values. Does like one population tend to produce bigger values than the other population? That's kind of what we're getting at without using the words like the mean or the average of this population is bigger than the mean or average of this population. We're just going to say this tends to produce larger values than this population, okay? So this is a non-parametric alternative to the t-test. In general, non-parametric tests are going to be less powerful than their parametric counterparts. So the Wilcoxon-Mann-Whitney is less powerful than a t-test, meaning if you can use the t-test, you should use the t-test, okay? Because if it's less powerful, then that means it requires more data to come to the same conclusion. You've got to gather more data just to make the same conclusion that the 2 groups are different, okay? But the reason for that is that it's making fewer assumptions about the sampling distribution. The t-test assumes the sampling distribution is normal, whereas the Wilcoxon-Mann-Whitney does not make that kind of assumption. And so in practice, this comes down to, you're going to use this Wilcoxon-Mann-Whitney test basically if the sample size is small, and with a small sample size, you know, we said a sample size is small if the population is normal. So basically the sample size is small and you have outliers in your sample, because if you have outliers in your sample, that's going to lead you to the conclusion that your population is not normal, right? If you have a small sample and there's no outliers, you might be able to get away with making the assumption that the population looks kind of normal, right? But if you have a small sample size and you have outliers, then you don't want to say, oh, I'm going to assume my population is normal, okay? So if you have small sample size and you have outliers in your small sample, Wilcoxon-Mann-Whitney is the safer test to use, okay? Wilcoxon-Mann-Whitney test is mathematically equivalent to another test called the Wilcoxon rank sum test, which, I don't know, depending on your studies in the future, if you take another kind of course, you might encounter the Wilcoxon rank sum test. Different process, but mathematically equivalent. All right, so we're gonna look at an example from the textbook, and apparently our scientists went to the forest and they decided to collect data on soil respiration. I don't quite know what this involves and what exactly this is, but apparently you can put something on the soil and you measure how much the soil is like breathing off carbon dioxide, okay? And you measure like how much, I don't know, air it's breathing, okay? Soil respiration. And they went to two different areas of the forest, right? There's this area where there's lots of stuff growing. That's going to be the growth area. And then they also went to part of the forest where like there wasn't much growing, and they said this is a gap in the growth, okay? And so the question is, you know, is the soil respiration quite different, right? Maybe the high growth is because of better soil respiration, or soil respiration is associated with whether there's growth or less growth or things like that. So again, we don't want to make conclusion. I want to avoid statements that involves things like saying the mean of this group or the mean of that group. So this is how we would phrase our null hypothesis. The population of soil respiration values for the growth area is not different from the population of soil respiration values in the gap area. Or maybe more succinctly, we can say both populations tend to produce similar values for soil respiration. The alternative would be something like this, that one of the populations tends to produce larger values than the other population. Or we would say there is a non-zero shift between populations. Okay, you could have directional alternatives, that the population from the growth area tends to produce larger values than the population from the gap area. Or you could say the population from the growth area tends to produce smaller values than the population of the gap area. So these would all be kind of suitable alternatives. And you'll notice that none of these alternatives you make use of the term mean or some kind of parameter. We're just talking about the population tends to produce values that are bigger and values that are smaller. These are very kind of vague statements, okay? So we don't use symbols like mu. Mu is a parameter, and this is a non-parametric test. And so we don't have a symbolic way to express these alternatives. We have to kind of use these long-winded phrases. All right, how do we go about doing the test? Well, what we're going to do is we're going to arrange the data in two columns from least to greatest, right? Population 1 goes in one column, or sample 1 goes in one column. Sample 2 goes in another column. And this is a little strange, is that for every value in for every single value, you're going to look at the other column and you're going to say how many values in the other column are less than this, okay? And if you have a value that's tied, you're going to give it a 0.5, okay? You're going to give it a 0.5. And you're going to sum up all of these counts at the end, and whichever one is larger is going to be your Mann-Whitney U value, okay? The Mann-Whitney U value. And then you're going to go to a reference table, which has a bunch of probabilities associated with these things. And so anyway, let's go ahead and do this. So the values from least to greatest, where did my numbers go? Okay, so we've got the values from the growth area, and we got values from the gap area, right? And I'm going to list them in two columns from least to greatest, okay? So the values from the growth area from least to greatest, 17, 20, 22, 64, 170, 190, 315, right? And so you can kind of see that when you look at these numbers, you're getting some really big values, right? Things that look like outliers, and you say, okay, well, maybe it's not safe to say this looks like a normal distribution, okay? And then when you go to the gap area, as far as soil respiration, the values that we collected are 6, 13, 14, 15, 16, 18, 22, and 29, okay? And it's okay that they have a different number of counts. So Y1 growth, we have n equal to 7, and over here we have n equal to 8, and that's fine. Okay, so what we're gonna do is we're gonna go to, for every value, we're gonna look at the other column and count how many values in the other column are less than this number, right? So how many values are less than 17? So we've got 6, 13, 14, 15, 16. We've got 1, 2, 3, 4, 5. So I'm going to put 5 values in the other column are less than 17. Then I go to the next value, 20. Okay, so I got 1, 2, 3, 4, 5. 18 is less. I've got 6 values that are less. Okay, the next value is 22. So these 6 values, and we have a tie. Okay, ties are going to be worth 1/2 each. So I'm going to do 6.5. Now, if I had 22 listed twice in this column, each one would be worth 1/2 point. And so then I would write something like 7. Okay, so each value that's a tie is going to be 1/2 each. Okay, and then at 64, I count and I go, oh, you know what? All 8 values are less than 64. And same with 170, same with 190, same with 315. Okay, and this thing where I write down 8 a bunch of times also kind of points us to, you know, the strengths and weaknesses of a non-parametric test. You know, an analogy could be that parametric tests, like the mean, is like business, and non-parametric tests are like sports. Okay, so in sports, it doesn't matter if one team, if you think of like a basketball game, it doesn't matter if one team beats the other team by 1 point or there's a blowout and they beat them by 50 points. Okay, a win is a win and a loss is a loss, whether you won by 1 point or you won by 50 points. Okay, but in business, whether you had a positive or negative quarter, right? If you had a bad quarter in business and, you know, at the end of the quarter you lost money, it's a big difference between losing $1 and losing $50 million. Okay, if you lose $50 million, you might not ever come back from that, and you might have to declare bankruptcy or get restructured or something like that. Whereas if you lose like $1 in a quarter, you know, that's not that big of a deal. You know, your investors and things like that probably won't be too upset. So the actual number that appears actually is important as far as business goes. And similarly, when you think about the mean of this column would be greatly affected by values like 315, right? This mean would get much bigger by the inclusion of using 315. But if you think about how does this translate into the calculation of our test statistic, this number 315 and this number 64 both contribute 8. You know, when we calculate the sum of these values, the sum of these values, 8 plus 8 plus 8 plus 8 plus 6.5 plus 6 and 5, this sum is going to be 49.5. This value, 315 and 64, both contribute 8 towards this sum of 49.5. Okay. So we do this, we go through every value, we count how many values in the other column are smaller. We're also going to do it just for good measure. With this, we're going to go through the other column. We're going to say how many values, we're going to go to 6. How many values in the other column are smaller than 6? Okay, no values in the other column are smaller than 6. And we're going to have 0, 0, 0, 0. At 16, we still have 0. And at 18, we have 1 value that is smaller. At 22, we have 1, 2 values and a tie, 2.5. And at 29, we have 3 values that are smaller. And so my sum here is going to be 6.5. Okay. So I've got two sums, and the larger value, 49.5, this is going to be my test statistic, 49.5. Okay. Okay, and what we're going to do now is we will go to our reference table. Our reference table requires that we have an n and we have an n prime, okay? The n is going to be the larger of the two numbers. We have two n's. We have a 7 and we have an 8. So my n is going to be 8, and my n prime is going to be the smaller of the two groups, 7. And we are going to go to our reference table. And we have a table for the Wilcoxon-Mann-Whitney. So table 6, critical values and p-values of u for the Wilcoxon-Mann-Whitney test. We're going to go to n equal to 8 and n prime equal to 7. And this is our row here, 40. Let me go ahead and I'm going to just copy this one row here. Okay, so here's my test statistic. And what, so the test statistics are these corresponding values here, 48, 50, 52, okay? And so if I had 50, it would be easy. My corresponding tail area is 0.0093, but I have something, I have 49.5. So a lot of times you might get the actual value. In this case, I got 49.5, and therefore my my tail probability, or actually, let me just go to the heading. The corresponding p-value for non-directional alternative is in italics. Okay, so I'll just go ahead and I'll see my non-directional p-value. Is between 0.021, so basically around 2%, and 0.0093. Right, so whatever our p-value is, it's somewhere between these two numbers, 0.021 and 0.0093. Okay, and that's for a non-directional alternative. All right, so I think I have all of this in your notes. Okay, so our non-directional p-value. So if we had chosen the non-directional alternative that said one population tends to produce larger values than the other, okay, so we would say our p-value, let's say our alpha is 5%, right? If n equals 8, n prime 7, the p-value for non-directional test is between 0.021 and 0.0093. If alpha is 5%, our p-value is less than alpha, we reject the null hypothesis. And we would say that we have evidence that the two populations produce different values. And furthermore, based on our data, we're going to say that the growth area produces larger values than the gap area, okay? Just because when we look at our data, so we come to the conclusion that they're different, and when we look at the data, we can say that the growth area produces values that are greater than the gap area. I realized I totally forgot about your view quiz answers. And we're actually gonna wrap up class a little bit early today. So I'll just go ahead and give you your last view quiz answers for today. Your last view quiz answers are, both of them are B. Your second one is B as in bear. And the third one is A as in apple. So today's second view quiz answer is B as in bear. And the third one is A as in apple. B as in bear, A as in apple. Okay, so that's what we would get for a non-directional alternative. If we have a directional alternative, right? So one directional alternative was that the growth area produces larger values than the gap area, okay? And so the p-value for directional test, and this one is the one with the correct direction, will be half of that of the non-directional p-values, right? So if you read this, the heading at the top of the table says directional p-values are found by dividing the numbers in italics in half. And so here we're at 8 and 7. We're going to take these numbers. We divide 0.021 by 2 and 0.0093 by 2. And so you get values like 0.0105, around 1%, and basically 0.00465, a little bit less than 1/2 of 1%. So if we have alpha equal to 5%, again, our p-value is going to be less than that. We would reject the null hypothesis. And we say we have evidence that soil from the growth area produces higher respiration values than soil from the gap area in the forest. Okay, and then the last possibility is you have the wrong directional alternative. Okay, so it's possible that someone says, I want to test the null hypothesis that the two areas produce similar values against the alternative that the growth area actually produces smaller values than the gap area. Okay, and so if you look at the data do not align with this direction, because you look at the sum from the growth area, the sum of basically how many values are smaller in the other column. This is bigger than the other value, right? 49.5 is a bigger value than 6.5. So, so this means overall, the values from the growth area are larger than the areas from the gap area. And we would just say we don't have evidence to support the alternative hypothesis that the growth area produces smaller values than the gap area. Okay. And that would be it. Okay, so we're going to just say we don't have evidence to support the alternative. We don't reject the null hypothesis in that case. Okay, we're going to end a little bit early today. We'll just wrap up the lecture here, and I'll let you guys go. So have a good weekend. You can expect to see the quiz posted, as usual on Sunday, and it'll be due Monday night. And we will see you guys on Tuesday. So have a good night and have a good weekend.